Good afternoon, class. Here's exam 4 review covering chapter 4, application of differentiations, chapter 5, integral 6.1 areas between curves, and now we're going to cover 5.2, the definite integral, 5.3, the fundamental theorem of calculus, for short, FTC. The definite integral. Suppose a continuous function f is defined on the interval of a to b. The interval is divided into n sub-intervals, delta x equals b minus a over n, and x sub 0 is a, x sub 1 is a plus delta x, and so on. Finally, b is x sub n, a plus n delta x. Then a Riemann sum associated with f is this following sum. The integral of a to b f of x dx is called the definite integral, which represents the area under a curve for a positive function, otherwise the difference of areas, and that's just the number, is the limit as n approaches infinity of the summation I going from 1 to n of f of x of I delta x. So the limit as n approaches infinity of f of x of 1 delta x all the way to f of x of n delta x, where delta x is b minus a over n, x of I is a plus I delta x, where x of I is any point in the subinterval of a sub I minus 1 and a sub I. Here's the definition. Let y or f of x be a continuous and non-negative over an interval of a to b. A definite integral is the limit as n approaches infinity, equivalently delta x approaching 0, of the Riemann sum of the areas of rectangles under the graph of y equals f of x over a and b. So the area under the curve has this definition, the integral of a to b f of x dx, or this limit, the limit of summation of I going from 1 to n of as n approaches infinity of f of x of I delta x. Delta x is b minus a over n, and x of I is a plus I delta x. And again, this represents the area if this is non-negative. Otherwise, it represents the difference of areas. Now, just to understand various parts of this definite integral, this is the integration symbol. The symbol was introduced by Leibniz and is called integral sign. It is an elongated S and was chosen because an integral is a limit of sums. Lower limit of integration, upper limit of integration, integrand, variable of integration, also known as dummy variable, because it is called a dummy variable because the answer does not depend on the variable chosen. The dx simply indicates that the independent variable is x. So the integral of a to b f of x f of x dx is a number. It does not depend on x. We could use any letter in place of x without changing the value of the integral. The integral of a to b f of t dt is identical to that. Or its approximation, the integral of a to b f of x dx is the summation of f of x of I delta x as I goes from 1 to n. That's an approximation, f of x of 1 times delta x all the way to f of x of n times delta x. This sum is called a Riemann sum. The precise value is when we take a limit and we let n go to infinity. The limit as n goes to infinity of summation of I going from 1 to n of f of x of I delta x. So the area in two different formats. This one is the limit of the sum, and this one is the integration. All right, so let's look at this example expressed as an integral on the interval of 0 to pi. The limit as n approaches infinity of I going from 1 to n, summation of x of I cubed plus x of I sine of x of I delta x. So let's compare it. So we said this is the definition of the definite integral of a to b f of x delta x. So as we compare these two, everything seems to be the same. So this must be f of x of I, and of course this is delta x. What about a and b? They are given as 0 and pi. So according to this, And then f of x sub I must be x sub I cubed plus x sub I sine of x sub I. And so that's f of x. A is 0, b is pi. So this limit is the same as this integral, put this one in here from a to b, 0 to pi. So the given limit, the limit as n approaches infinity of summation of I going from 1 to n, x sub I cubed plus x sub I sine of x sub I delta x, is the same as integral of 0 to pi, x cubed plus x sine x dx. What about this one? Expressed as an integral, the limit as n approaches infinity of summation of I going from 1 to n of sine of 2 pi over n, 2 pi over n on 0 to pi, which is obviously a to b. So again, let's do the comparison to what we have. This and the limit. So clearly, a 0, b is 2 pi. And delta x is b minus a over n. So let's write it. This is it. And that means 2 pi minus 0, or simply 2 pi over n. X sub I is a, 0, plus I times delta x. That makes it 2 pi I over n. Simply multiply this one by I. So f of x sub I, so you compare, f of x sub I is this, right? Sine of 2 pi I over n. From 0 to 2 pi. And therefore, the limit as n goes to infinity of summation I going from 1 to n of sine of 2 pi over n times 2 pi over n, this one, is the integral of 0 to 2 pi sine x dx. So all you have to do when you compare, figure out the function, f of x is sine x, and figure out the lower and upper limits, a and b. So that's just the setup. Now, what about the evaluation? Use summation formulas to compute the integral of 0 to 2, 1 minus x squared dx. And of course, we remember the formula, the integral of a to b f of x dx is this limit. So having said that, there are a few things that from algebra will be helpful. I'm going to remind you. The summation of 1 is n as I goes from 1 to n. So if it was, let's say, 5 would be 5. The summation of c would be nc. So multiply by nc. The summation of I as I goes from 1 to n is n times n plus 1 over 3. Similar to arithmetic sum. The summation of I squared as I goes from 1 to n is n times n plus 1 times 2n plus 1 over 6. And the summation of I cubed, in essence, is this one to the second power, n squared times n plus 1 squared over 4. So having said that, we're going to use that as we need it. So let's work on this integral using the summation, although ultimately we use the easy way out known as FTC. But for now, f of x is 1 minus x squared. A is from 0 to 2, a is 0, b is 2. So delta x is b minus a over n, which means 2 over n. X sub I is a plus I delta x, which means 0 plus 2i over n, or 2i over n. So if f of x is 1 minus x squared, what is f of x sub I? 1 minus x sub I squared. What is x sub I? 2i over n. So 1 minus x squared. Replace the x with x sub I, which is 2i over n quantity squared. So we are going to write this summation. We're going to simplify it, then we put it inside the limit. So we're going to work on this. I'm going to write this, everybody. The summation, I going from 1 to n, of f of x sub I, this piece, times delta x this piece. Now, the idea is to expand and figure out what it becomes according to what we have here. So having said that, let's distribute here. This becomes 2 over n. This becomes 4i squared times 2, 8i squared, n squared times n cubed. That's basic math. So one more time, 1 times 2 over n, and then 4i squared over n squared times 2 over n. Now this one, I can take 2 out, 2 over n, and put summation of 1, because it is I that moves from 1 to n, nothing else. And this one, I'm going to take minus 8 over n cubed out, but I have to keep the I squared in. So anything involving I, because this is I, everybody, anything involving I remains. So now all you have to do, replace this one with n, replace this one with this. That's it. Now, this is clearly 2. It's not a big deal. Now, this one, I want you to see that this is n cubed, and we don't even need to know the rest of it. I'll tell you why we don't need it in a moment. So we are going to write of course 2n cubed, because this is n, this is n, this is 2n. 2 and 8, the product is 16. So 2 minus 16n cubed over 6n cubed. Why is it we don't need that? Because now I'm going to put it into the limit. So let me take the limit of this expression. So the integral of 0 to 2, 1 minus x squared dx is the same as limit of this expression, as then goes to infinity. And because this is a rational expression, because the degree of, you have to divide by highest degree term in the denominator, namely n cubed, because they are the same, this becomes 16 over 6. So the answer is 2 minus 16 over 6. Two minus 8/3 is negative 2/3, and we're done. Very straightforward, everybody. A quick recap. So we use the formulas, and into the limit, we put f of x of I and delta x, and we simplify such that we can use this. Given f of x equals x cubed minus 6x, evaluate the Riemann sum, taking the sample points to be the right endpoints. A is 0, B is 3, N is 6. So first of all, here's the graph. And here's number 3. And we want this. Okay. Just to let you know what we are interested in is this. This. And by the way, you can clearly see that this is larger than this one. So you expect a negative value because this represents the different subareas. If we want the area, we have to take the absolute value. So having said that, here's the function. A is 0, B is 3, N is 6. So delta x is B minus A over N. 3 minus 0 over 6, or 1/2. So a line segment from 0 to 3, an easy way out. A starts with 0, B ends with 3, and in between we add 0.5, 0.5, 0.5, or just 1/2. So those are the endpoints. And if we were to graph this, we'll show that this is the part we want. For example, this one, you can calculate the area, this one, this one, this one, this one, and this one. All of them have the same with delta x of B minus A over N, which we found it to be 1/2. But what is the height? So we use the right endpoints. That means we use all the endpoints except the first one, because we want to use the right endpoints. That means f of 0.5 for this one, which becomes this height and this rectangle. Then f of 1 plus f of 1 and so forth. So R6, why R? Right endpoints. Why 6? Because we are using n equals 6. Half, why 1/2? This is delta x, everybody. This is delta x. F of 0.5 all the way to 3. So, for example, if I want 0.5, is 0.5 cubed minus 6 times 0.5. F of 1 cubed with the minus 6 times 1, and so forth. I put it in, I calculate it, I end up with negative 3.9375. Note this value represents the difference of areas, and I can't emphasize this enough, because if it's positive, it's the area under the curve. Okay, if the function is positive or not negative for that matter. Now, what about evaluating this, which gives you the exact value? Again, we are going to look at the easy way out for that later on, which is using the FTC, fundamental theorem calculus. But for now, to do that, we are going to go with A is 0, B is 3, delta x is B minus A over N. So this is the area we want. Again, same area, okay? So that's the function. A is 0, B is 3, delta x is B minus A over N. 3 minus 0 over N. X sub I is A plus I delta x. And A is 0, simply I times delta x. Again, remember, we want this area. So this integral is equal to this limit. And f of x sub I is f of 3i over n, and delta x is 3 over n. So again, we are going to work on this. When we are done and simplify this, then we put it into a limit and we take a limit. So let's work on that. So what is f of 3i over n? X cubed, 3 over n cubed, minus 6x minus 6 times 3i over n, and times 3 over n. So I hope everybody can see what's happening here. So this one, I'm going to replace the x with 3i over n and take it from there. Now this is 27i cubed over n minus 18 over n times I. I'm going to distribute the 3 over n. This is 3 times 27, 81 over n to the power of 4 times I cubed. We keep the I cubed in, the rest outside. This 2 minus 54 over n squared, we just keep the I inside. So I hope you see why I'm writing it this way, because this one, now I can replace it. And this one, I can replace it. So what matters here is that we have n squared and some other stuff. So 81 n to the power of 4 and some other stuff, minus 54 n squared and some other stuff. Why? I don't care for the rest, because I want to put this into the limit. So the integral is equal to this limit, everybody. And when we have a limit as n approaches infinity, and it's a rational expression, they have the same degree. It's just 81 over 4, the same degree, 54 over 2. So 81 over 4 minus 54 over 2. Let's change this to 108 over 4, and we end up with negative 27 over 4. And we're done. Now, later on, we'll see that we can make it much easier by using FTC, as we are going to move on and do that also in the next example. So having said that, What about this one? It says evaluating integrals using signed areas. Use the signed area to interpretation of the definite integral to compute the integral of -1 to 2x dx. In other words, you want to graph it, and now you're dealing with the geometric shape that you can figure out the area. You don't need um, what we have been doing so far. So first and foremost, the function is f of x or y equals x in the interval of a to b, -1 to 2. Now, f of x equals x or y equals x is a line that goes through the origin from -1 to 2. This is -1, this is 2. We want this area, this area. Now, please understand, the way this works is the difference of area. So the area of the green minus the area of the red triangle. And we know it's a geometric shape of familiar. It's a triangle. So the area is 1/2 base times the height. So we can easily calculate it. This point has coordinates 2, 2. This point has coordinates -1, -1, which means for the green one, the base and the height are 2. For this one, 1. So the green one is 1/2, 2 times 2 or 2. The red one is 1/2, 1 times 1 is or 1/2. And this integral is the difference of the areas, 2 minus 1/2 or 3/2. Very easy because it's a geometric shape and we can handle it. What about the fundamental theorem of calculus? Well, according to FTC, one of them is that the integral of a to b, f of x dx is capital F of b minus capital F of a. Find any antiderivative, and you don't need a constant, evaluate it from top to bottom. So plug in the top minus plug in the bottom. So x, the antiderivative is half of x squared. We're going to evaluate it from the bottom -1 to top 2. So 1/2, if I put 2, 2 squared is 4. If I put -1 squared is 1. So 1/2 times 4 minus 1, and it's absolutely the same answer that we got here. So what is the difference and why is it important to understand this? If it's not a geometric shape such as this one, where we can use a formula from geometry, what do? We use calculus. Graph and use signed areas to show that the integral of -4 to 6, -4 to 1, 6x dx is -45. I'm giving you the question, I'm giving you the answer. I highly recommend you try it to make sure that you understand how things work out here. Use geometry to evaluate the integral of -3 to 3 square root of 9 minus x squared dx. At this point, the only way we can handle this is by recognizing what we are dealing with here. So the function is this, square root of 9 minus x squared, and the interval is this, -3 to 3. Okay? So that's the first thing we should recognize. Then I want to remind you, when we are dealing with the circle centered at 0, 0, x squared plus y squared equals r squared, if it's had a center at hk, x minus h quantity squared plus y minus k quantity squared equals r squared. So, and of course, the area is pi r squared, the circumference is 2 pi r. Needless to say, we are dealing with the area. So y equals square root of 9 minus x squared. I hope you realize if I square both sides, I get a circle centered at 0, 0 with the radius 3. And by the way, just reminding you, the top half is the one with the positive, square root of 9 minus x squared. The bottom half has the formula with a negative in front of it. Okay. And let me erase this. The right half, x is equal to square root of 9 minus y squared. The left half, this portion, the same thing with a negative in front of it. Okay, just to let you know how things go. In any event, So it looks like this. So you calculate the area, pi r squared, and it's a semicircle, half of it. So the graph of G is a semicircle of radius 3. So 1/2 pi times r, which is 3 squared, 9 pi over 2. It's very simple. And we don't have any method in calculus 1 to solve this except this. In calculus 2 is a different story. We have a method to solve this. For calculus 1, there's absolutely no other method. Properties of definite integrals. Let f and g be continuous functions over the interval of a to b. The definite integral at a point, the integral of a to a f of x dx is 0 simply because it doesn't cover any area, or you can say delta x becomes 0. Sum and difference. The integral of a to b f of x plus minus g of x dx, you can cut them into two pieces. The integral of a to b f of x dx plus minus the integral of g of x dx from a to b. So this piece and this piece, we can add them up. Scalar rule. If you have a constant multiple, you can take it out. Think about this. This is f of x. This is 2 times f of x. If f is larger than g from a to b, doesn't matter where, we're just talking about a to b, the integral of a to b f of x dx must be larger than or equal to integral of a to b g of x dx. So if f is at top of g, it covers a larger area, assuming they're positive, right? Bounding, max and min. If the function f of x is between its minimum value lowercase m and maximum value uppercase m, from a to b, again, it doesn't matter what happens outside. So m times b minus a less than or equal to the integral of a to b f of x dx less than or equal to capital M b minus a. You can see it here. So here's the function, the area under that. Here's the minimum value, the rectangle, the green one. And here's the maximum value, this rectangle that has this height, which is larger. So that's clear. Splitting additivity, the integral of a to c f of x dx is the integral of a to b f of x dx plus the integral of b to c f of x dx. Okay. In other words, go from evaluated from a to b, evaluated from b to c, add them up is the same as evaluating directly from a to c. Opposite rule, the integral of a to b f of x dx is negative of integral of b to a f of x dx because delta x becomes negative now. The integral of a to b c dx is c times b minus a. It's just because c is what? It's just the horizontal line. And if f is larger than or equal to 0, from x equals a to x equals b, the integral of a to b f of x dx is larger than or equal to 0. Now, let's use those properties for the following. We have the integral of f of x dx from 1 to 3, 3 to 7, and 1 to 3 for g of x. And we want to evaluate the integral of 1 to 3, 3 times f of x dx. So if this is 6, just multiply it by 3, and you get 8. What about this one? We're going to cut it into two pieces, 2 of this minus 4 of that. So 2 times 6 minus 4 times minus 4, 12 and 16, 28. 1 to 7, well, 1 to 3 plus 3 to 7. So the integral of 1 to 3, f of x dx plus the integral of 3 to 7, f of x dx. And so this is important. They are obviously identical. So we have the sum of 6 and 9, 15. What about the integral of 3 to 1? Is the same as 1 to 3, but negative. So it's the opposite of that, minus 6. We simply use properties as mentioned. FTC, the fundamental theorem of calculus. The fundamental theorem of calculus is appropriately named because it establishes a connection between the two branches of calculus, differential calculus and integral calculus. It gives the precise inverse relationship between the derivative of the integral. The d dx of the integral of a to x f of t dt is f of x. In other words, if you integrate some function of t, let's say, f of t dt, from some number, any number, doesn't matter what number, up to x, and you differentiate it with respect to x, you get the same function back evaluated at the upper limit, which is the new independent variable. So the fundamental theorem of calculus. Suppose f is a continuous function in the interval of a to b. If g of x is the integral of a to x f of t dt, then g prime is f of x. That's exactly what it says here. The integral of a to b f of x dx is capital F of b minus f of a. We just did that in the previous page where f prime is lowercase f. Okay, so those are called, and this is another way of writing it. These two are the same. FTC, there are two of them. Sometimes they call this one number one, this one number two. Sometimes the other way around. It doesn't matter. All right, the integral of 0 to 1 x to the power of 7 dx. Now that we know FTC, we don't have to go with the limit. Okay, the limit is tedious, but it's important to know it. And so you take the definite integral, and that means 1 over 8 x to the power of 8 from 0 to 1, and plug in 1, plug in 0, you get 1 over 8. Please understand the following tip. Even if we use another antiderivative, capital F of x plus c. In other words, if you put plus c here, in the evaluation theorem, the result will be the same because capital F of b plus c minus capital F of a plus c, they cancel out the c. So even if you put a c, they cancel out. What about the integral of 1 to t x to the power minus 1? Please understand x to the power minus 1 over 1 over x is the same. It's a natural log. You have the absolute value. Because the limits are positive, you can lose the absolute value. This is 0, so you get precisely ln2. Whereas this one, again, we get the same answer, natural log, but both limits are negative, and we must keep the absolute value because ln of -1 means nothing because the domain is from 0 to infinity. So ln of -1 is undefined. So this is ln1. Which is 0. This is ln2. So minus ln2 is the final answer. What about the integral of 0 to pi sine x dx? Remember, the derivative of sine is cosine, but the integral is negative cosine. So we're going to evaluate the negative cosine from 0 to pi. I like to put the negative outside, and we're going to plug in. Now, as you know, cosine of pi is -1, minus cosine of 0 is +1. So these two give us -2, negative outside makes it +2. What about this one? First and foremost, notice this is t, therefore 1 gives you t, cosine gives you sine t. Remember, the derivative is negative, but the integral is positive. Plug in power 2 and 0. As you know, sine of 0 is 0. This goes to 0, power 2 is fine, sine of power 2 is 1, and the final answer is power 2 plus 1. It's an exact answer. What about this one? First and foremost, use your algebraic technique to change this to x to the power of 1/2. This has exponent 1. 1/2 becomes 5x to the power of 3/2. Now it's an easy anti-differentiation. 5 times what? 5 divided by 3/2 plus 1, x to the power of 3/2 plus 1. 3 divided by 1/2 plus 1, x to the power of 1/2 plus 1. And as I mentioned, we don't need a constant because it goes away. So now we have 5/2. This is 2, 3/2. This is 2. We're going to plug in 4, we're going to plug in 1, and we're going to evaluate. This is elementary algebra. Let's quickly go over that. 4 to the power of 5/2. 2 to the power of 5, 32. 2 times that, 64. 4 to the power of 3/2, again 2, 2 cubed 8, 2 times 8 is 16. And I hope you see that this entire thing is 4. So 76 is the final answer. Evaluate the integral of a piecewise defined function, the integral from -2 to 2, where f of x is defined as 2 between -2 and 0, 4 minus x squared, when x is between 0 and 2. And so from -2 to 2, even if they had mentioned from negative infinity to 0 and 0 to infinity. Because this is limited from negative 2 to 2, we cut it into two pieces. From negative 2 to 0, we use this one. From 0 to 2, we use this one. So two pieces. That's really the idea behind this. This gives you 2x from negative 2 to 0. This gives you 4x minus 1/3 x cubed from 0 to 2. And believe it or not, let me put asterisk next to it. This is the only calculus step. Now you're going to plug in here. You get 2 times 0 minus 2 times negative 2. This one is 4 times 2 minus 1/3 times 2 cubed. And when you plug in 0, it becomes 0. So this becomes 0 and it has no bearing. Okay. And of course, this is 4. This is 8. We have 12. This is also 8. 12 minus 8/3. And 12 is 36/3. We get 28/3. Find the derivative of this function where g of x is the integral of 0 to x squared of 1 plus t squared dt. So the function f of t is this, and it's a continuous function because 1 plus t squared from 0 to infinity. Remember, on the radical must be positive, and 1 plus t squared is actually always positive from negative to positive infinity. So let me just write that. The domain would be 1 plus. So by FTC, G prime is the same thing, plug in X. What about here? Now, the derivative, the d dx of the integral of f of t dt, if it goes from a to x, we know what that is. But if this is a function of x, then we get f of g of x times g prime. This is by the chain rule. So the function here is sine t. So it will be sine of this upper limit. If the upper limit was x, we would be done, but it's not, times its derivative, which is 2x. Now I want to show you why it works in case you want to go the other way around and you want to use that. So the integral of 1 to x squared sine t dt, sine becomes minus cosine t from 1 to x squared. First evaluate this, then we're going to differentiate this. So minus, plug in, you get minus cosine x squared minus cosine 1. And bear in mind, cosine 1 is just a number. So we have minus cosine squared plus cosine 1. Now I want to differentiate this. Differentiate this. This one has no bearing, becomes 0, because it's a number. So the derivative of negative cosine is positive sine. The same thing, x squared by the chain rule times 2x. So even if you go that route, that's actually a proof that it works, okay? What about this one? The same thing. The function, so the d dx of the integral of 1 to x squared plus x tan t dt, the function is tan t. So you are going to replace the t with x squared plus x. If it were x, we would be done. It's not, and therefore we need g prime of x. We need the derivative 2x plus 1. This times 2x plus 1, put it in front, and you're done. What about this one? If the lower limit is a number, that's the answer. What if the lower limit is not a number, is a function? So it can be shown that the derivative of the integral of g of x to h of x f of t dt is f of the upper limit, h of x times h prime of x, just like before, but minus f of g of x times g prime of x, because the bottom is now a function. So therefore, how do we start here? Please understand the function is t squared. So plug in the upper limit, you get sine squared. And because it's a function of x times its derivative cosine x, minus f of g of x minus tan squared. times the derivative of tan x secant squared. Just by this one and you're done. It's very simple. The dx of 1 over sine x, uh, the integral of 1 sine x to 1 square root of 1 plus t squared dt. First and foremost, this is your function f of t. Okay. And you are going to, because we know from a to g of x, we are going to interchange them, and then we have to negate that, therefore. From sine x to 1, we can write from 1 to sine x, but notice we change the sign. And now f of t is the square root of 1 plus t squared. So we are going to replace the t with sine x. So minus is outside, square root of 1 plus sine squared x, and then the derivative of sine cosine x, and we rewrite it. This is the final answer.